Okay.
Before we dive into today's topics, here's a quick review of what we did at the end of last week's session, the ARL exam review website. And just to make things easier, I added a few slides with information about what you need to do to get in.
Oh,
So,
Barb, we can see you now.
I'm out of here.
We were
hi,
working on
Barb.
There's Barb.
So just a couple of slides to show you where you need to click and what you need to do in order to get into the exam review and take practice exams and practice the questions for the chapter. Did anybody do the questions for chapter 2? Yes, great. So if you run into problems, here are the slides. And again, I will send them out tomorrow so that you can use these few screenshots to navigate your way through the exam review site. So today we'll talk about radio and signals fundamentals. This is pretty important stuff. It is what ham radio is built upon, and there unfortunately are a few things that may be a little bit harder to understand, but we'll try our best to walk you through the process, and at the end you should be able to answer all the questions on the test. So you may know that when it comes to engineering, we don't use units like miles and feet and gallons and quarts and ounces and fortnights, furlongs and other strange units. We use the metric system. And the metric system comes with its very unique set of prefixes that indicate how big a certain number is. So when you go down this list of prefixes here, tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, pico, some of these may sound familiar to you because you've probably encountered them before. If you've ever been to Canada, chances are you know what a kilometer is. So the kilo that we use as a prefix in kilometer is actually an indication that we're dealing with 1,000 meters. The same thing if you look at your medicine cabinet and look at the ingredients on aspirin, ibuprofen, or any other medication that you may have in your medicine cabinet, the amount of the active ingredient is very likely specified in milligrams. And milli, again, is one of those prefixes that we need to deal with. When you look in the middle column, you see a symbol, T, G, M, K, H, and so on. These are important as well, and we will need to practice a few of those. There are a number of questions that reference some of these. And then the last column, this is where it gets complicated. We see the multiplication factor. And if you don't have a mathematics or an engineering degree, this may look pretty scary, but believe me, we can make this work without too much math. So here is a chart that I tried to convey how you convert from one thing to another thing. So I said a kilometer is one of those things. So we have kilo, which, let me just bring up my pointer. Can you see this?
Mm-hmm.
Okay, so the kilo is here. And we see the relationship between a kilo and the 1 is we either multiply by 1,000 or we divide by 1,000 when we go the other way. So a kilometer is 1,000 meters. A milligram is a 1,000th of a gram. So we always work with a multiplication or division by 1,000 when we go from one of these prefixes to one of the neighboring prefixes. So a giga is 1,000 megas. A mega is 1,000 kilos. A kilo is 1,000 ones. The one is 1,000 millis. A milli is 1,000 micros.
Okay.
A micro is 1,000 nanos, and so on. So I think you get the gist. It's pretty simple when we just make one step, one jump. It gets a little bit more complicated when we do two jumps. How do we get from 1 to mega? We multiply by 1,000 and then we multiply by 1,000 again, and that is 1 million. So when we do two jumps, it's multiplying by 1 million or dividing by 1 million.
So
Now,
it's adding or subtracting a zero?
it's adding or subtracting 3 zeros, or moving the decimal point by 3 places. It may make more sense once we do some examples for this, but the good news is there's only a very limited number of questions on the test that deal with this. So if you remember the answer to those 3 or 4 questions that deal with these prefixes, you are golden. And chances are, once you actually start using this, converting from megahertz to kilohertz, for example, because you have a radio that displays information in kilohertz, and you have a listing of frequencies that use megahertz, it gets pretty easy once you do this a few times. So here are a few examples. And again, it doesn't matter what type of value we deal with. The prefixes are always the same. They behave the same way. So I have a few examples here. Here we have megavolts. What a volt is, we'll learn about next week. The important thing is that it's a mega. So this is 1.2 megavolts, which is the same as 1.2 times 1,000 kilovolts. Because when we go from a mega to a kilo, we multiply by 1,000. So here is that multiplication with 1,000, and we end up with 1,200 kilovolts. When we have 3.2 kilowatts, again, ignore the W. We don't care about what it is right now. The important thing is the kilo at the beginning. And if we want to convert this to watts, we go from kilo to the 1, which means we multiply by 1,000 one time. So it's 3.2 times 1,000 watts, which is 3,200 watts. And here are a few more of these examples. The last one is actually one that is from the test. They want to know what 1 million picofarad is in microfarad. So in this case, we do two jumps. We go from pico, which is all the way over here. We do 1, 2 jumps to micro. So it involves multiplying or dividing by 1 million. And we already have 1 million picofarad. So we divide that by 1 million, we end up with 1 microfarad. So this weird character that you see down here and that I pronounce micro is actually a Greek character. It's a Greek letter mu. And we use that to indicate that we are dealing with 1 millionth of a unit. So a 1 millionth of a farad is 1 microfarad. Does that make kind of sense? I don't expect you to be able to convert random numbers left and right, going from and to, and doing 3 and 4 jumps. All I want to understand is whether the process makes sense to you. I see one nod.
Give a thumbs up or a nod, or, you know, I would just add that when I was first introduced this, when I took the class last year, it like blew my mind and hurt my brain and made me want to cry. Even though I knew it, you know, 40 years ago, I knew it, but I got myself all in a twist, like I really needed to understand it and I needed to do it. And then I realized that there were 4 or 5 questions and all I had to do was memorize the answers, and then I relaxed.
And I actually have a few more samples for you where you can practice at home. And then if you run into any problems, we can come back to this next week. So Greek letter mu, or micro. So we've used some of these units now, volts and watts. We'll go into more details about what these are next week, but just to give you some background, these units are usually named after a person. And I have a list here that shows you what the unit is, what we measure with it, and what it was named, who it was named after. This is not on the test, just for those of us who like to dig a little bit deeper. Sometimes that's some additional information. So here are some more examples that you can do at home. I am listing again the source and what we want to convert it to. So the 2.5A for ampere, which is here on this list. When we convert this to milliamps, how many is that? Any guesses? I know you all know it. You're just too slow hitting that unmute button.
2,500?
Yes, it's 2,500. So play around with this at home over the next week and see if you can get the hang of it. And again, once we go into the questions, you'll see there really are only a handful of those unit conversions, and you have them down in no time. So having that out of the way, we can now really start with radio fundamentals. The most important thing that we deal with when it comes to radio in general is a radio wave. And in order to get a better idea how radio works, we need to be able to talk about waves in a way that allows us to capture the main characteristics of a radio wave. And because of that, we need to learn some vocabulary that may be new to you, at least in the context of waves. So I have a little picture here that shows you a wave, and we all know waves. When we go to the beach, there are some waves. Up here at Lake Ontario, they are pretty small. If you've been to an ocean, you know they can be bigger. You may have seen a wave at a football stadium when the people in the stands are doing the wave. It's exactly the same idea as a radio wave. So it doesn't matter what kind of waves we deal with, sound waves, ocean waves, the waves in sporting stadiums, or radio waves, the idea is always the same. So when we look at this wave, we see that something is going up and then going down again, going to the negative maximum, going up again, going through the 0 point again, going up to the positive maximum. And this is going on until you turn the radio off. So the amount of how far this wave goes up, we call the amplitude. So if we have a wave that has a higher amplitude, that could mean that a signal becomes louder. But in general, it's stronger. So closer to the antenna, you would have a larger amplitude than 1,000 miles away from the antenna when you transmit. So the amplitude indicates how strong that wave is, how far up it goes as at its positive and negative maximum. Then we talk about frequency, and we measure frequency in hertz over here, abbreviated with a capital H and a lowercase z. And the frequency basically counts how often we have one of these swings up and down and back to the neutral mark within 1 second. So with an ocean wave, it's really easy to do this with just your watch. You count how many seconds it takes from one wave crest to the next wave crest, and then you say, okay, this wave has a frequency of 1/10 of a second because it takes 10 seconds until the next wave arrives. With radio waves, it's a little bit faster, and a stopwatch will not do as much good. We are talking about 1 million of these up and down movements within a second. So we need some sort of machinery to measure that. We won't go into any details how we would do that. The important thing is we count how often that wave goes up and down and then returns to the neutral point within 1 second. So we call this one cycle, and then we count how many cycles we can fit into 1 second, and that is our frequency. We can also go the other way around, and again, with a stopwatch, we can measure how much time it takes for that wave to go from this neutral point up, through the neutral point down, and then back again. And we measure that in fractions of seconds or seconds, and we call that the period of a wave. And then we need to understand what fundamental and harmonic frequencies mean. This becomes important when you are actually turning your transmitter on, because even though you want to transmit just on one frequency, there's a pretty good chance that you have other frequencies in your output signal. That one frequency that you want to transmit on, we call the fundamental frequency. Let's say 7.150 megahertz, which is 7,150,000 hertz. That's where you want to transmit on, but there's a pretty good chance you will also have twice of that frequency in your output, and 3 times and 4 times that frequency, just with smaller and smaller amounts, and we call these the harmonics. So multiples of the fundamental are the second harmonic, the third harmonic, and so on. And this is important because the FCC tells us how much of these harmonics can be in our output signal for it still to be considered a clean signal. When these harmonics get too large, then you have a dirty signal, and the FCC might send you a nasty letter. So again, we have the amplitude, which is how tall that wave grows. We have the frequency, how many of these up and down movements we have within one second. We have the period where we measure how long it takes to go from the neutral up and down and back up again. And then we have the harmonics, which are the second, third, and fourth, and fifth, and so on, multiples of our fundamental frequency. Any questions about that?
So is the fundamental, could you call it like the beginning frequency?
It's the frequency that you actually want to transmit on.
Okay.
So that's the frequency that you dial in on your radio. And that's
Okay.
what the radio displays. The radio would not display your second, third, and fourth harmonic frequencies because you don't want to transmit those. You want to keep them away from the antenna, but it's not
Okay.
always possible. So they sneak through. And how they do that, you'll learn when you study for your extra class license.
Okay, thank
So
you.
we don't need to know about that. It's just we need to understand the terms. If somebody talks to us about a second harmonic, we say, okay, this was my original frequency times 2. So if the original frequency is 10 megahertz, the second harmonic is 20 megahertz.
Okay. Okay, thank you.
You're welcome. So now that we have a little better understanding of what a wave is or how we would describe a wave, let's now concentrate on radio waves. So we leave the ocean waves alone, the audio waves, sound waves, and all the other waves, and we look at radio waves. And radio waves are actually electromagnetic waves. So we don't really talk about radio waves. We talk about electromagnetic waves. And that term describes the physics behind those waves. So we know what electricity is. At least we have a rough idea about it. We have an outlet somewhere in our room. We plug a lamp in. There's electricity coming out of the outlet and making that lamp light up. So we have a rough idea about what electricity is. We know magnets. You put them on the fridge and they stick. So what is an electromagnetic wave? Now, if you look into the physics of electricity and magnets, you'll actually find that you can convert one into the other. So if you have an electric current that flows somewhere, there's a magnetic field involved. We don't have to know about that. The important thing is that one can get converted into the other and back again. And that is actually what happens with our radio waves. We have two different types of fields. We have an electric field and we have a magnetic field. And the electric field grows and breaks down again. And during that process, it creates a magnetic field that grows and breaks down again. And that breaking down of the magnetic field again creates another electric field. So we have these two fields going back and forth. And again, you don't have to know about all the details, how this actually works. The important thing is that we have these two different types of waves that together make up our electromagnetic or radio waves. These waves vary in intensity based on a sine wave, and we've seen a sine wave here. So this is a sine wave. It grows, goes to the top, slows down when it comes close to the top, and then speeds up again, goes down, slows down again, goes around the curve, comes back up. So these are sine waves. And if we had a way to visualize these electromagnetic waves, that is what they would look like. What is important is that they travel at the speed of light. And there are a couple of questions about that on the test. Here's a little bit more about what actually happens. So I said electricity can be converted into magnetism and the other way around. When we have electrons moving in our antenna, when we try to transmit, we're pumping electricity into that antenna. And that then creates this electromagnetic wave that spreads out from the antenna. and then has a life on its own. Independent of the antenna, it just travels through space and hits another antenna, where this then gets done in a backwards process. That electromagnetic wave induces a current, a movement of electrons in our antenna, and that current then, the electric current, can then be received and amplified by a radio. Again, there are no questions on the test about that. This is just to give you a rough idea of what we are dealing with when we push that push to talk button on our radio. Now, this is where it comes important again, because what we will talk about now will be on the test. You know about the FM and AM commercial radio spectrum. When you get in your car, you turn the radio on, you can switch back and forth between AM and FM. And we know FM stations sound better. And AM stations, usually you can listen to for a longer distance when you drive out of Rochester. So pretty good chance when you listen to a Rochester radio station and you drive on the thruway, you pass Victor. And a few miles after Victor, that FM station is just noise. When you turn on your AM radio at night, there's a good chance you can listen to a station from Chicago. So we have different kinds of radio spectrum that behaves differently. And in order to talk about these different areas, we call them by a certain name. So we group frequencies that behave in a similar way together, and then we describe them with a different name. And here are the names that we use for this. So when people first started to name these things, they had an area that they called low frequency, one that they called medium frequency, and then one they called high frequency. And they said low frequency is from 30 kilohertz to 300 kilohertz. And here are those prefixes again that we talked about at the beginning, kilo. Then we have medium from 300 kilohertz to 3 megahertz. Different prefix. If you know how to convert your megas to the kilos, you know that 3 megahertz is 3,000 kilohertz. So we go from 300 kilohertz to 3,000 kilohertz. And then HF high frequency was from 3 megahertz to 30 megahertz. And that was it. That's what we had. And then somebody came along and said, hey, I can make higher frequencies. And they called those frequencies very high frequency, 30 megahertz to 300 megahertz. And that was good for a while. And then somebody else come along and say, hey, I can make even higher frequencies. And then they scratched their heads and said, what the heck do we name them? And they named them ultra high frequencies. So those physicists really are very creative when it comes to these names. So ultra high frequencies are 300 megahertz to 3 gigahertz. Another prefix, 3 gigahertz, is 3,000 megahertz. So our UHF, or ultra high frequency range, goes from 300 megahertz to 3,000 megahertz. And then they kept on making faster and faster, higher and higher frequencies, and they called them super high frequencies and extremely high frequencies. But we don't have to deal with those. The ones that we deal with are high frequency, very high frequency, and ultra high frequency. So again, the radio waves within one of these groupings behave in a similar way. How exactly? We don't care at this point. We'll talk about that in week 4 when we talk about propagation. What is important for this go around is that we remember these boundaries: 3 megahertz to 30 megahertz, 30 megahertz to 300 megahertz, and 300 megahertz to 3 gigahertz. So there are 3 questions on the test that ask about that. So you may have noticed that there's always a factor of 10 involved when we go from the lower boundary to the higher boundary. So 3 megahertz to 30 megahertz is a factor of 10, 30 to 300 megahertz is another factor of 10, and 300 megahertz to 3 gigahertz, same thing again, factor of 10. And that may make it easier to remember those boundaries. Here's a little bit more about names of commercial bands. So as I mentioned, the AM band, the FM commercial radio band, the CB band, these are all bands that we kind of know what they are. We can look up what their frequencies are, and they are named for what type of use you will find in those bands, in those frequency areas. Like the AM band is the AM broadcast band. You find AM broadcast stations in there. WHAM, WXXI, WCMF, all the ones that you find on the dial when you spin. Actually, the ones that I just named were actually FM radio stations. No, actually, I did a mix. HAM, WHAM is an AM. The other 2 were potentially FM. So never mind. So the important thing is we group them by usually what type of services we find in those bands. And that is true for commercial types of bands. When we come to ham bands, this is all different. So in the ham bands, you don't find just one type of signal, like an AM signal. What that is, more about that later. We are able to use all different sorts of signals in our ham band. And that is very different than what you find in all the other bands that are out there controlled by the FCC. So we again have more power, more flexibility, more freedom to do whatever we want to do with our frequencies within certain boundaries. And again, with that comes the need to actually take the test and show that you know a little bit about radio and what it all involves. So here are a couple of examples for the ham bands. We have a 40-meter band, a 2-meter band, a 70-centimeter band. And again, here are the prefixes, centimeter. That's one of those prefixes that we talked about in the beginning. We'll talk a little bit more about how to define the amateur radio band in a couple of slides down the road. What we'll do now is take a closer look at what radio signals actually are. So when we look at a radio wave that is not just on, you turn it on and it's not doing anything. If you change that wave somehow, it can carry information. And by making a radio wave carry information, we are forcing it to occupy more than just one frequency. When we look at this little picture here, which is actually a picture of what the AM commercial broadcast band may look like. So there are broadcast stations here, and you see they are not just one frequency, they're spread out a little bit. They start here, for example, a little bit before 800 kilohertz, they go to 800 kilohertz where they peak, and then they go a little bit further. And you may have noticed that when you tune on your AM radio, the different stations are actually in 10 kilohertz distance from each other. So you wouldn't find a radio station at 805 kilohertz. There would be one at 800, and there would be another one at 810, and the third one 10 kilohertz lower, 790. So that conveys that this is not just one frequency, but it gets spread out a little. When you tune your radio, you can hear how a station is starting to come in, and then you turn to the middle of that spread out region that is associated with this radio station, and this is where you have the best and the strongest signal. When you tune a little bit away again, it gets distorted, it's not as strong. So a receiver is tuned by putting it right on that center frequency of that spread out AM signal. And just to relax you a little bit, here are some pond waves. This is exactly the same as with a radio wave. When you see that pond wave spread out in a circular fashion around where that rock hit the water, that is exactly how our radio waves spread. If you have a single vertical antenna, they go into all directions with the same strength, just like the wave on the pond. So when you get this presentation tomorrow, you can click on that button as long as you want, as often as you want, and look at those relaxing ripples, just to take your mind off those crazy metric prefixes that you have to learn. So any questions about radio waves so far? Okay. So we know about amplitude, frequency. Now we throw another thing into those ways we can describe radio waves, and that is the wavelength. So the definition of wavelength is that it's the distance a radio wave travels during one cycle of the wave's electric and magnetic field. When we go back to our little video here, so when you look at one of those ripples, how it is moving away from the center, you could potentially take a ruler and measure the distance between one peak and the next peak. And you would have the wavelength of that pond wave. The same thing goes with radio waves. If we had a way to visualize radio waves, with a little bit of spray paint in the air, and they would all of a sudden manifest themselves out of thin air, we could measure from one of those maximums or minimums to the next one, and then determine the wavelength of that radio wave. We use the Greek letter lambda as a symbol for the wavelength. So when you see a formula that has a lambda in it, there's a pretty good chance it's talking about wavelengths. Now, if you look into the physics of this, you can actually figure out, when you know the frequency, you can figure out what the wavelength is if you know how fast it is spreading out. And does anybody remember how fast a radio wave travels?
The speed of light?
The speed of light,
It's the
yeah.
speed of light, yes. So with that, you can actually determine what the wavelength of a radio wave is. And to save you some time to look this up, it's right here in this little diagram here. Lambda, or the wavelength, is the speed of light. We use the little lowercase c for that, divided by the frequency. And if we want to simplify this a little bit, we can say lambda is 300 divided by the frequency in megahertz. That gives us the wavelength in meters. So over here, we have one of those examples. We have a frequency 50 megahertz. So we plug that into our formula here. 300 divided by the frequency in megahertz. So 300 divided by 50 gives us 6 meters. So the 6 meter band is around the 50 megahertz mark on our radio dial. So 6 meters is actually a ham radio band, and it is 50 megahertz and up. So that little formula here is, again, on the test. They want to know how you convert from a frequency to the corresponding wavelength, or the other way around. So it's 300 divided by the frequency in megahertz gives you the wavelength in meters, or 300 divided by the wavelength in meters gives you the frequency in megahertz. So we can also do 300 divided by 6 meters gives me the frequency of 50 megahertz. That's the same diagram, just bigger. More description of that wavelength. So we go from one peak through the valley up to the next peak, and that is our wavelength. So here we have a table that shows different ham radio bands and their frequencies. So again, we divide 300 by the frequency in megahertz, and that gives us the wavelength in meters. The bands are here on the left side, on the right side. We have the 160 meter band, the 80, the 60, the 40, 30, 20, 17, 15, 12, 10, 6. It doesn't stop there. This is just when I ran out of page. So there are more bands available to us hams, but I just stopped there because this is what you would find on a typical HF high frequency receiver or transmitter. So I have here on the left side a frequency in that band, and then we do the calculation 300 divided by the frequency gives us the wavelength in meters. So in this case, we end up with 166.67 meters, but the band is called 160 meters. So our band description is actually just the approximate frequency, the approximate wavelength in meters. It's not exact. It's just so that it's easy to say, oh, I was on the 160 meter band. You don't have to say I was on 166.67. So it makes things a little bit easier. Same thing for 80 meters. When we look at the frequency, we actually end up with 85.7. The 60 meter band is a little bit below that, 56.28. Here we have the 40 meter band, 41.67, and so on. So again, the band description is just the approximate wavelength in meters. There's a question about that.
Hey, Karl-Heinz, I have a question about
Yeah.
that slide.
Mhm.
I noticed that when you talk about the wavelength and when you talk about the band, you normally just round it up to the nearest or round it down. Is that how it works?
Yeah, you have established ham radio bands. And these are the ones that you find in the right column. That's what they are called. So you have the 40-meter band, the 20-meter band. When they first came up with that, they just used whatever they came up with mathematically and went to the nearest round number. So you have to go back more than 100 years to figure out exactly who was responsible for that and who did that. But that's what they did. They just picked a close enough number that was nice and round.
Okay, I do notice that the 41.67 is rounded to the 40-meter band, but then the 10.5 wavelength is rounded to 10. So one kind of rounded the other way.
Right. It's just going to the closest reasonably round number. Now, one thing you may notice is that with some of these bands, we have a relationship. We have the 160, we have 80, 40, 20, 10. So it's always half of what we started out with. We start out with 160, then comes 80, which is half. Also happens to be twice the frequency. From 80, we go to 40, it's half the wavelength, but twice the frequency. 40 to 20, half the wavelength, twice the frequency. So the original ham bands are the ones that follow that structure. Going back 100 years, that's what they had. And then the ones that don't fit in, they were added at a later time. So some of these names go back to that old relationship that they had when ham radio was young. And you may remember we talked about fundamentals and harmonic frequencies. This is based on those harmonic frequencies. So I said you want to transmit on one frequency, but your radio will also emit some of those harmonics at a much lower level. So you transmit, for example, on 1.8 kilohertz. There is a harmonic on 3.6 kilohertz, which also happens to be in the 80-meter ham radio band. So you are only interfering with another ham. You are not interfering with emergency services, for example. So the attempt was to put those harmonics into ham bands so that we just mess with our fellow hams and not with something really important.
Gotcha.
But as the transmitters got better, we were actually able to filter out all those harmonics, or most of them. So that allowed us to add some bands that don't follow that nice divide by 2 or multiply by 2 pattern.
Got it. Thank you.
You're welcome. So it may sound pretty confusing to have to deal with bands and frequencies, but believe me, once you start to play around with your radio, it'll become second nature. And you know that 7.15 megahertz is in the 40-meter band. You don't have to do the math in your head anymore. You just know that it's the 40-meter band. So don't worry about that too much today or tomorrow or within the next 10 weeks. Once you actually get to use this, it will become second nature to you. Now, one interesting fact you may have noticed is when we go up in frequency, our wavelength is getting shorter. So the frequency increases, the wavelength is getting shorter. Or the frequency decreases, the wavelength is getting longer. And that is one answer to a question on the test. That relationship, the frequency decreases, wavelength increases, or the other way around. You need to know that for the test. When you open your book, you may have seen this chart. And it may look pretty confusing if you don't know what you're looking at. But this actually lists your privileges on the amateur radio band. In addition to that, it also lists all the bands that hams in general, not necessarily you as a technician, but hams in general in the US can use. So I started my table here with the 160 meter band, and I ended with the 6 meter band. But you see there are actually 2 bands below 160 meters. And there are bands well beyond 6 meters. So for the first few, they have these little graphics. And then down here, we have a whole bunch of bands listed where we just say, okay, do whatever you want on those bands. And when you look at the key here, you can see what you can do. So with a technician class license, you need to look for the T. When we look for the 40 meter band, for example, we find the T here. When we go over here, we see all these squiggles. We look for the squiggles and it says CW only. CW stands for continuous wave, which is ham speak for Morse code. So on the 40 meter band, you can use Morse code as a technician. And there are some of these HF bands have privileges for you carved out. The interesting thing is once you get to 6 meters and higher, there is no distinction anymore between an extra, a general, or a technician. You have exactly the same, or you will have exactly the same privileges as somebody with an extra class license on 6 meters and higher. That, I think, is also a question on the test. So we've mentioned the speed of light a few times. The test, of course, wants you to prove that you know what the speed of light actually is. So what is the speed of light? It's 300,000 kilometers per second, or it's 300 million meters per second. And I think the test is asking for 300 million meters per second. We'll see what the exact test question is in a little bit, if we get to them. So that is something, that is a number that you need to remember. We're almost done with our topics for today so that we can dive into the questions. So this is all we had about waves, radio waves. Do you have any questions about what we've done so far? Don't see any hands waving, don't see anybody unmuting, so I think we're good. For the first week, they want us to learn about 2 radio-related terms. The first one we need to learn about is the transceiver. So before we can understand what transceiver actually means, when we look at a radio, it consists of a number of different parts. You have a microphone, you may have a Morse code key, you have a loudspeaker, you have an antenna, and then somewhere in between all those parts that are attached to the radio, you have a receiver, which is what you use to listen to things, and you have a transmitter, which allows you to transmit a signal. And in the olden days, you actually had two different boxes. There was a box, a big metal box on your table that was a receiver, and that only was a receiver. It could not transmit. Your box next to it, there was a transmitter, and it could not receive. And you needed to switch back and forth between those two when you wanted to switch from listening to somebody to actually talking to somebody. And if you've ever seen the movie Frankenstein, you probably know that Professor Frankenstein or Dr. Frankenstein has this big knife edge switch on the wall that he flips, and then he's alive or it's alive. These switches were actually used to switch between the transmitter and the receiver. A little bit of radio history here. We don't do this anymore. With the advancement of technology, it's now possible to put everything into one little box. And if you've ever seen a handheld radio, it can be very small. No manual switching back and forth between receivers and transmitters. And they came up with a new name for these devices, and they call them transceiver, which is a unit that combines the function of a transmitter and a receiver. So we take trans and ceiver and mush them together and come up with transceiver. So this is an answer to a question on the test, a unit combining the functions of a transmitter and a receiver. The second thing they want to learn us about in this unit is what a repeater is. So if you have one of those little handheld radios, they are not very powerful. And yes, if you go to a sporting goods store and look at how they advertise these little radios, they probably tell you about 50 miles of range. Forget it, doesn't work that way. Maybe if you are flying at 30,000 feet and use one of those, but not on ground level. So these radios are not very powerful, and the signal from them only travels as far as you can see. And we call that line of sight propagation. More about that in 2 weeks. Usually the antenna you have is also very inefficient. So low power, being on the ground, inefficient antenna means your signal will travel maybe a couple of miles, 3 miles. On a really good day, up to 7 miles. And then the curvature of the earth gets in the way, and that's it. So how do you talk to somebody from one end of town, across town, to the other end of town? Or from up here in Rochester down to Naples, you use a repeater. What is a repeater? A repeater is a more powerful radio in a very good location that's beneficial to line of sight propagation. Usually a mountaintop, on a tall tower, on a tall building. So when you drive around town and look at tall buildings, usually you see antennas on top of those buildings. These are not radio antennas for the people living in that building or working in that building. These are oftentimes cell phone antennas. They are cell towers, even though they're not really towers, or you find repeaters. So a repeater is a radio in a really good location that allows you to reach maybe 50 miles around the repeater site, and it can receive the signal from your little handheld radio. And then it amplifies that and sends it out again, much stronger than your little radio could be, so that other people with other little radios 50 miles away can then hear you talk. So a repeater allows us to extend the range of our radio. And it does that by receiving on one frequency and retransmitting that signal on a different frequency. And the difference between those frequencies is called the repeater offset. There is a question on the test, I don't think in this, in the questions related to this chapter, but there is a question on the test about repeater offsets. Repeater offsets are also important when you try to program your own radio. If you want to find out about local repeaters, if you already have a radio and you want to listen, you cannot transmit without a license, but you can listen. This link has a list of all the local repeaters, or it's referring to a spreadsheet with all the local repeaters. The page also has information about local nets, what that is, more about in week 6. So these were the 2 radio-related terms that we needed to learn this week. Any questions? Yes, Erin.
Yeah, I have a question. Okay, so is it comparable, talking about the handheld radios and how they're marketed to go a lot farther than they actually do? So Verizon cell site, let's say, now this is 10 plus years ago, would actually, one cell tower would go 5 miles. So if you're saying this radio could potentially reach 5 miles, does that mean that a cell phone on a Verizon tower uses a similar type of technology to go more than 5 miles, or handoff between tower and tower? That you're saying that these small, well, I'll stick with the small radios because that was the example you used, and that's about the range of a 10-year-old cell phone tower. Does it use similar technology with repeaters and whatnot for your handheld cell phone to do what these handheld radios can do? Sans your own equipment?
It is similar technology, because when you talk from one cell phone to a different cell phone, the cell tower always is involved. You're not talking directly from your phone to my phone. It goes through the cell tower, even though when we're standing right next to each other.
Okay.
So that is similar to what a repeater does.
Okay.
The only difference is that our radios can actually talk to each other directly. So we don't need the repeater if we are close enough.
Okay. Okay. And it can use more frequencies than a cell phone, whereas Verizon might own the 700 megahertz spectrum. Your radio can actually access, I mean, not saying a cell phone can't access more, but on a Verizon network, it's only going to access. And then our radios can access different frequencies that our cell phones per se wouldn't be able to. So, and the radio wouldn't necessarily need some of the stuff that your cell phone would need.
Right.
Okay. Okay, that helps me to
So
understand.
we don't need infrastructure out there provided by somebody else to talk to each other. Now, if we do have that infrastructure in form of a repeater, we can talk easier across a bigger distance. But because we have all these frequencies available here on this chart, we can actually pick and choose a frequency at any given time of day during the year throughout the 11-year solar cycle, where we can say, with a very good chance, I can make a contact from here to any point on the Earth by having all these frequencies available. Now, it may not work every day, but it will work eventually. So the sun is spitting out material towards the Earth every now and then that cuts radio signals out completely. During a time like that of a solar storm, you would not be able to make many contacts on a worldwide basis.
Okay.
But in general, with all those frequencies that we have available, we can pick and choose the frequencies that we want to use at any given point, and we can, with a high likelihood, make a contact without having to use anybody else's equipment.
Okay, and I know that I have one more question that might pertain to this. Let me know if it doesn't. So e-com, the technology and the phones that are used when electronic communications go down. I know that we were talking about how emergency communications for hams become important when things like your mobile cell phone carrier has a service outage of some sort due to whatever reason it might be, a solar storm, an outage, a technical problem, a hurricane. E-com, let's say these devices are protected, like the shielding and the cabling, for instance, from electromagnetic frequencies, weapons, whatever it might be. So these things are shielded in certain ways. Is the reason, so e-com is, how is e-com related to ham, if at all? Because e-com devices are supposed to be able to work through these types of emergency disaster situations to keep people in communication. Is that similar to ham technology or related in any way?
There are, if we look at the Red Cross, for example, they have some of their own communications equipment that they can use in an emergency, but they may not have enough or not enough in certain locations where all of a sudden there's a big need.
Okay.
So in those cases, ham radio can assist those official emergency communications protocols.
Okay.
That is why in a few weeks, we will learn about 2 different emergency communications groups within ham radio. One is on the government side, working with the government, assisting the government in emergency situations. The other one is on the civilian side. So in order to work with the government, there are training requirements and all sorts of red tape associated with it. But at the end, you as a ham would use your ham radio equipment and on amateur radio frequencies to provide assistance in these emergencies.
Okay.
In addition to whatever other communication equipment those organizations may have.
Okay.
Now, if this is something that you're interested in,
Yeah.
when you
Yeah.
get your license, join the ARIES or RACES organizations. These are the 2, and we'll talk about what they are in a few weeks, and there are actually questions on the test about them. So we have 2 local groups that do this, and they are always looking for volunteers.
Okay. Okay. But so that technology is something you would assist with, but not necessarily use. So those frequencies, or should I just wait? Will I get to know more about it?
This is actually not subject of the technician's test. So we don't go into
never mind.
into any details about how it all works. So if you really want to know more about that, get in touch with those groups.
Okay. All right, great. Thank you.
Okay, so the idea now is we'll go through as many questions as we have time for. I have all the questions from the question pool in my presentation. So if we don't get through all of them, they will be there for you to take a look. They are also in the book. They are in the book at least twice, in the front, in the chapters, and at the end in the official question pool. And of course, they are all in the exam prep website. So you should be able to see them whenever you want to see them and practice them as often as possible. So I would recommend that we all unmute ourselves now, unless there's a loud dog in the background or a TV blaring. And then you just yell out the answer and let me know whether you know something or not. But also let me know if you studied for a certain question and you just cannot understand why a certain answer is the right answer. So what is the name for the distance a radio wave travels during one complete cycle? Does anybody know the answer?
Wavelength.
What was that?
Yeah.
Wavelength.
The wavelength, yes. So this is exactly how you would see the question on the test. It's the exact same question that would show up on the test. The only difference is that the order of the answers, the potential answers, is always randomized on the test. So if you see, in this case, the right answer is C, wavelength, don't bet on it that it will be C wavelengths on the actual test. It may be A wavelengths or D wavelengths. So you need to recognize wavelengths, not the position of where the answer was when you did your practice tests.
And lots of the questions have ways to remember it, like distance and length. Like if you go back,
Yes.
you know, distance is not speed, distance is not form or spread, it's distance is length.
Yeah, little tricks like that will help you to come up with the right answer. So how fast does the radio wave travel through free space?
At the speed of
Anybody.
light.
Only one at a time, please. Otherwise, I can't hear the right answer. I assume that two of you said at the speed of light at the same time, and I just could not understand it. So again, this is one of those things we just need to know. Radio waves travel at the speed of light, which is not the speed of sound. It's way too slow. The speed is not inversely proportional to its wavelength. There was something else about wavelengths and inversely proportional. That was the frequency, not the one here. And it does not increase as the frequency increases. So it is the speed of light. You just have to know that. Oh, and some of these questions, you will find the reference to the question in the question pool at the bottom of the page. So how does the wavelength of a radio wave relate to its frequency?
Here's another tip for the test is, especially at the beginning as you're studying, reading through all the answers, because you might think the first one or the second one is it, and reading them all will keep you from getting messed up.
Also, sometimes the right answer is all of the above. So if you just say, oh, I know it, this is, A is the right one, you may actually miss that there are two more right answers, and because of that, all of the answers is the correct answer. It's not very frequent that that is the right answer, but there are some questions where all of them is the right answer. So again, how does the wavelength of a radio wave relate to its frequency? So we said,
Nice job, Gail.
The wavelength gets shorter as the frequency increases. Yes. So one goes up, the other one goes down in numbers. And now we are talking about the formula, how we can convert from frequency to the approximate wavelength in meters. And what is the formula?
This one tripped me up because I know it's 300. What did you say?
D.
Frequency to wavelength. 300 million, because I remember thinking that's a good dollar amount to have. So something about 300 million.
So is it C? Is that the answer? I'm guessing because he's not saying anything that that's not it.
Okay, so the wavelength in meters is 300 divided by the frequency in megahertz.
And the way I would remember that is it's the one that doesn't line up, because all the A, B, and C are wavelength in meters equals frequency in. All three of those are the same, and D is different. And that's how my brain works.
But for us with a more mathematically equipped brain, it's 300 divided by the frequency in megahertz.
If you have a
and
lazy
it's important
brain,
that it's important that it's a frequency in megahertz. So it's not the frequency in hertz.
So why did I remember 300 million? Because I remember purposely remembering that number. So meters and mega.
300 million was the speed of light, 300 million meters per second.
Per second.
And if you use that, then the formula is actually 300 million divided by the frequency in hertz.
Okay.
So
Okay.
we have the megas both with the 300 and with the frequency, and that allows us to get rid of that. So we end up with 300 divided by the frequency in megahertz.
Okay.
So which property of radio waves is often used to identify the different frequency bands? Does anybody remember any of the bands that I mentioned, ham radio bands?
Yeah, they went from like 30
Okay.
to 300, right?
These were the frequencies. The bands are actually the 20 meter, the 40 meter,
Yeah.
the 80 meter, the 2 meter. So what is that we used?
The approximate wavelength.
It's the approximate wavelength, yes. So remember that table with all those not very nice looking numbers? We rounded that to something closer, and we said, okay, the approximate wavelength in meters is what we call that band.
Okay, so those are bands, and then the other ones were frequencies or wavelengths.
You're probably referring to this one.
Okay.
We are talking about the VHF, UHF, or HF spectrum boundaries.
How does the spectrum relate to the band? How does a band fit into a spectrum?
Okay. How far back do we have to go? When we look at this chart here,
Mm-hmm.
Do you remember the boundaries of the HF spectrum?
3 to 30
Yes, 3 to 30 megahertz.
megahertz. Okay.
So when we look at these, there are some frequencies associated with this. So this is 1.8 megahertz. So this is not part of the HF spectrum. Down here we have 3.5 megahertz. That now is larger than 3, so that is HF. 7 megahertz, okay, 10, 14, 18, 21, and so on. 28 megahertz. This actually ends just before 30 megahertz. So everything from here to here is in the HF spectrum. So the 80 meter band, 60 meter band, 40 meter band, and so on up to the 10 meter band are in the HF spectrum.
Okay.
After that, we have the VHF spectrum, very high frequencies, goes from 30 to 300. So we have the 6 meter band, the 2 meter band, the 1.25 meter band.
Okay,
These
so
are in the
bands
VHF.
they divide up the spectrum.
Yeah. So
Okay,
there are
so
smaller allocations, smaller frequency allocations within one of those spectrum ranges. Now we share this HF spectrum with a lot of other radio users. You find broadcast, shortwave broadcast stations in the same areas in between the ham band. So there's, for example, a 49 meter broadcast band, which is between 40 and 60 meters.
And is that the distance that it travels, or is that the distance? Does it have anything to do with that at all?
If we could see the radio waves in the air around us,
It's going to be.
it would be from one of those hills
Yep.
through a valley up to the next hill. And we would take our tape measure and measure that distance.
Okay.
And that would be approximately 40 meters for a signal in the 40-meter band.
Okay. So it actually does relate to the distance that it actually travels.
Yes.
Exactly. Okay.
So again, the ham radio bands are just smaller allocations, frequency allocations within one of those spectrums, the HF, VHF, UHF,
Okay.
high frequency, very high frequency, ultra high frequency. So going back to this question, so what are the limits of the very high frequency spectrum?
So it would be 30 to 300
Megahertz, yes.
megahertz.
Yes.
Megahertz,
So
yes.
because
megahertz.
30 to 300 is also here. If you just go for the numbers, you
Oh,
might pick
clever.
the wrong answer. This is kilohertz, this is megahertz. So it's important to actually not just look at the numbers, also look at the unit with the prefix. So yeah, 30 to 300 is correct. 30 to 300 megahertz. And now the same for the ultra high frequency spectrum.
I have to cheat, so I won't answer.
Anybody else?
Checking in your book is not cheating. It's just all different ways of letting it get into your head.
Okay.
You're not expected to have all of these things memorized today.
So let me give you a tip here. None of
Yes.
these numbers that we are dealing with are kilohertzes. So that already rules out two of these answers. So A and C are not the right answer because they are dealing with kilohertzes. So that leaves 30 to 300 and 300 to 3000. What was 30 to 300?
The one we
VHF.
just did.
It was the one we just did, which was the VHF.
Very high,
Very
not ultra.
high.
And ultra would be
Mhm.
like high, like 300, ultra high. So that's a higher number. And even though
Yes.
in the book it says it's gigahertz, 3 gigahertz, 3000 megahertz will be 3 gigahertz. So it will be
You've
300
got it.
Exactly.
You got it exactly, Aaron. They're tricking you because when we looked at it on the band plan,
Mm-hmm.
it switched. It went from 300 megahertz to 3 gigahertz.
But this is why it's important to know some of these prefixes and know how to convert from one to the other.
Right. Here's
Okay.
another hint that I used when I was studying, and that was I went in the back of the book and I looked at all the questions that were about the spectrum. There's 3 questions, and they're always the same. And you just drill on those 3 questions, and then that's it. You're done. You don't ever have to think about the spectrum again because you know there's only 3 questions and you know the answer.
Okay. Okay. Yeah. Because this is confusing to me because I'm so stuck on and it's bringing back I haven't worked at Verizon in so long and that's all I can think of. So the only way I can try to bring my brain to understanding something different is to compare it to it. So sorry, everyone, for the Verizon cell phone comparisons.
Okay.
But I see there's a mobile phone band in the ultra high frequency. So it doesn't seem to relate too much to ham. Like the mobile phones seem to be totally different.
With these spectrum ranges that we are now talking about, these are not ham specific.
Oh, okay.
So as I said, we share the HF spectrum with, for example, commercial radio broadcast stations. Shortwave broadcast stations are right next to us. And there are other users in the HF spectrum. The military is a big user of spectrum in general.
Mm-hmm.
So you find them everywhere, interspersed with ham radio. So this is the third question about those spectrum ranges. So we had VHF, UHF, now we're talking about HF. So again, you can rule out one of these right away because we said we're not dealing with kilohertz. So what do you think is the right answer here?
Three to 30 megahertz.
It's 3 to 30 megahertz, yes. So these are the three questions that talk about these spectrum boundaries. HF 3 to 30 megahertz, VHF 30 to 300 megahertz, and UHF 300 to 3000 megahertz. These are the only ones you need to know.
Okay.
And if you've seen them 5 times by doing practice tests, chances are you'll have them down.
Do you guys have a, oh, can you guys hear me?
Yeah.
Oh, do you guys have a good way of memorizing this? Like a mnemonic or something?
Karl-Heinz, go back to the first one, the answer, not the question.
This one?
So the way I did it was, I remembered, which one's first, Karl-Heinz? Is it UHF or VHF? High frequency.
The sequence goes high frequency, very high frequency, ultra high frequency.
So
and they all
HVU. And this, I'm telling you, this is, I swear to God, this is how I remembered it. There's some TV show called SVU. It's CSI or something like that, SVU. And this is HVU. So in my mind, I knew what the numbers were. And whenever I heard, which one is it? In my mind, I went, oh, right, SVU, Special Victims Unit, but it's HVU. So I did high, very high, and ultra. And I know it's crazy, but for some reason, that's what stuck in my brain was SVU. Or an SUV vehicle, it's not that, because that's, anyway, crazy. I don't know if that helps, Ian, but crazy things like that is what I was doing.
And the other thing is, they're always times 10. So the lower number is the other way around. The upper number is 10 times the lower number. And we start out with
just that
3.
there's so many threes in it, and then there's a bunch of zeros, so it's gotta be that somewhere.
Right, so the smallest is 3 to 30. The smallest is 3 to 30, so that's the first one. So that's the high. The next one is 30 to 300. So that's the middle one, which is very. And the biggest number, 300 to 3000, is the ultra. It's the biggest.
Okay.
Yeah. And believe me, in the next couple weeks, you're going to know, just like Karl-Heinz said, you are so going to know these.
By doing practice tests, you will see these answers again and again and again. And eventually you'll get the reflex down to say, yep, that's the right answer. So just to throw a few more numbers at you, what is the approximate velocity of a radio wave as it travels through free space?
300 million.
Yes, 300 million meters.
There's your 300
Not
million.
dollars.
But it's not, is it meters or is it miles? Is it B or is it C?
Meters, because
Per
we got to
second.
focus on driving in Canada when we're thinking about this stuff.
Yes, yes.
Exactly.
Actually,
we
I'm
never
from
deal with
Canada.
miles. We never deal with miles when it comes to science. So it's 300 million meters per second. So again, they are throwing in the same number again, just to confuse you. But because we know it's never miles, we can eliminate 2 of these options right away. And then it's 150,000 kilometers per second or 300 million meters per second. And we know the speed of light is 300 something.
You're going to remember that Aaron was like, I know something is 300 million. And so you're going to remember that.
It was the only dollar amount that made
Yep.
sense in terms of, hey, that's reasonable to have, and hey, that's a lot to have. Everything else was like, and that was how I remembered it. I mean, not that I would ever have that much money, but you know what I mean? Like,
One could dream.
right, right.
Okay, now we're going back to the waves. What describes the number of times per second that an alternating current makes a complete cycle? So now they're throwing in alternating current. We haven't talked about current yet, but I said a wave is a wave is a wave. So it doesn't really matter what we are dealing with, the amplitude, the frequency, the period, the wavelength, all these things apply to every kind of wave. And we can deduct from that what we would call the number of times per second that an alternating current makes a complete cycle, what that is. So what do you think is the right answer here?
Frequency.
It's the frequency, yes.
Was it? No cheating.
And I would think the number of times is the clue for me on this one, that frequency means how often and number of times means how often.
Okay.
And for some of these things, you can say, okay, after week 10, we've never talked about pulse rate. That term never came up, so just eliminate it right off the bat. And that always makes things easier if you can cross something off and say, I don't even have to consider that. That is clearly wrong. That narrows it down and then makes it easier to pick the right one. So yes, it is the frequency. What's the unit of frequency?
Hertz.
It's the hertz.
You know that it's not Tesla because we haven't talked about that. So you could rule that one out. I don't think that Tesla comes up anywhere in
No, no, it does
technician
not.
class.
It does not. This is something that I have not mentioned, but it's mentioned in the book. What does the abbreviation RF refer to?
Radio frequency.
It's radio frequency signals of all types. So it doesn't matter whether it's HF, VHF, UHF, or any of the other spectrum regions. It's all RF, all radio frequency signals. Okay, and here come the questions about unit conversions. Which of the following is equal to 500 milliwatts? So milli is one of those prefixes. And if we, it's an easy way to jump back.
Wait a second. Before you jump back, oh, I was going to say, it's always moving the decimal point 3 places. And only one of those answers had the decimal place moved 3 places.
Okay, now I don't find my spot
Clover,
anymore.
Clover, have you done some of this stuff in school, some of the decimal places, and have you done any of that stuff yet? Okay. So, and Annika, I imagine you guys are good with this because it's fresh in your brain. So if you move that decimal point, it's after the second 0, right? Because it's 500 point nothing. And you move it 3 places. That way.
We can rule out one of these options right away because the numbers are different. We need to see a 5 somewhere. And when we see a 2, this is wrong. It cannot be A. So milli, you may recall, is a 1/1000th of something. So 1 milligram in your pill that you take is 1/1000th gram of whatever the active ingredient is. So there are 1,000 milliwatts in 1 watt. Does that help you come up with the right answer?
It would have to be 0.5 because it's the only one that's over 3.
Right.
But that's the only way I knew to know that was the 3. I don't think I have it in my little head yet, like either that or
Well,
it's
you
been so
don't have to
long.
have it in your head. All you
Okay.
have to do is move the 3.
Okay.
Because you get, if you move it 2 points, if you move it 2 places, you get 5. If you move it 1 place, you get 50. But it's always 3. You always
Okay.
move it 3.
Why is it always 3? That's just how their system is set
That's
up.
the
Like,
1,000. That's the 1,000 part.
okay.
It's multiplying with 1,000 or dividing by 1,000.
Okay, which
But
would
again,
go back to.
If you go through those sample questions associated with this chapter 5 times, you'll just pick half a watt out of that mix without any problem.
And we're going to
Okay.
do them all right now. There's only a handful of them. It's like we already did all the VHF, UHF ones. Now these are the math ones. So there's
Okay.
one. What's the next one?
The next one is, which of the following frequencies is equal to 28,400 kilohertz? So again, we look at these numbers, we see B here, different digits. We are looking for 284. There is 280. It cannot be B. So 28,400. If we move the decimal point,
Put your cursor back where the decimal point really is. It's down at
here.
the other end. No, that's the comma. Go the other way.
oh, here. Yes,
Yeah.
that's what I mean.
So
it's
you
here.
move it 3.
So 1, 2, 3.
And then it would have to be megahertz because we're going equal to kilohertz.
Yes.
So it can't be another kilohertz. So it has to be the megahertz.
Good catch,
They
Aaron.
try to
Yes.
trick you.
Good catch. They try and trick you between A and D.
Okay.
Excellent
Yeah.
catch.
So
Everybody see that? Do you guys see that? You good with that?
So this was the second question with unit conversions. Here is the third one. How many milliamperes is 1.5 amp? How many milliamps in 1 amp?
So do the thing with, well,
The 3 decimal points, C.
Did you
So-
say C?
Mhm.
Yep. 1, 2, 3. 1.5 amperes is 1,500 milliamps. So again, there is 1,000 millis in whatever one unit we have. So you can also just say 1.5 times 1,000 when we want to go to milliamps. Gives me 1,500.
and you don't even have to pay any attention to whether they're milliamps or amps because it's all about moving 3 decimals. And if you go one way and the answer isn't there, then go 3 the other way until you see the
Thank
answer.
you.
What is another way? I think this is number 4 now. What is another way to specify a radio signal frequency of 1,500,000 hertz?
So you're going to move the decimal point 3 places. So you got 2 choices now. And this is another one where they want to trick you. This is one where you really do have to remember the picture with all the circles that Karl-Heinz made.
So we know it's when we move the decimal point by 3 positions, we end up here. So it's not C and it's not D. So is it A or is it B?
Okay, so would it be megahertz?
I choose A as an apple.
Oh, no. I was guessing.
What do you guys think? It's definitely not hertz. What, in the order of things, what comes, is a kilo bigger or smaller than a mega?
I don't know.
Well, even just listening to the word, like a kilo,
Mega sounds bigger.
mega sounds big.
How? Yes, mega sounds bigger. How many
So
meters
next
in a
Letter is
kilometer?
capital.
How many meters in a kilometer?
Yeah.
1,000.
Yes, 1,000. So kilo is 1,000.
How do you get that? Okay, say I drive in Canada a lot. How did you get kilo as 1,000 from driving on the QEW, let's say?
You have to know how many meters are in a kilometer.
I don't know. I just go the speed limit and hope that I'm looking
Right.
at the right one on my speedometer.
So hertz is small, kilo is the next size up, and mega is the next size after that. So we only went from hertz, we only made one jump.
Okay,
So we
that's
went from
okay.
hertz
So
to kilo
this
to
is
mega.
kilo. This would be mega.
Okay,
1.5
okay.
mega or 1,500 kilo.
Does the fact that the M is in capital letters indicate that it's larger than the little k, the lowercase k?
In general, yes, because there's also a lowercase m, which stands for milli.
Yep. Okay,
Now, there is no capital K. The capital K stands for Kelvin, which is a temperature. So we
okay,
don't want to get into that. But it's important that it's a lowercase k. There's actually one question that asks about that. So the
okay.
K is lowercase. The M can be uppercase or lowercase, depending on whether it's mega or milli.
So what's
Okay,
the
so
answer?
The first A.
Yin already said it was A, yes. One more. How many volts are equal to 1 kilovolt? So again, we have the kilo. What did we say means kilo?
1,000.
1,000. So which makes this answer Karen, it looks like you're talking, but you're muted. You can just push the space bar that will unmute you temporarily.
Okay, it's because I'm not sure I'm right. Is it 1,000 volts?
Yes, it's 1,000 volts.
I would have
So
been wrong.
Kilo means 1,000. So
Oh,
1
yeah.
kilovolt is 1,000 volts.
So if you were doing a kilometer, that'd be 1,000. What's a mile?
1,000 meters. Yes.
Meters,
A kilogram.
meters, miles, meters.
A kilogram is 1,000 grams.
Okay, a kilogram is 1,000 grams. So a kilogram would be like your medicine, you said?
No, that would be the milligram. A kilogram would be 2 pounds. You don't take 2 pounds of medicine usually.
And
No,
you
I probably
guys,
couldn't. Okay.
keep in mind that he grew up with this. Like Karl Heinz loves to bake. That's one of his hobbies in addition to ham radio. And our kitchen scale is in grams. And that's how he thinks because that's how he grew up.
Okay.
And like for me, I was in school a long freaking time ago. So I have to wrap my head around this stuff.
I'm a paper writer. I have a degree in political theory. So testing was not my thing. So, so your answers, Susan, like your ways of like thinking about the answers are so helpful, just so you know.
Okay, I think we are almost done with these questions. So here is another one, and this time we are talking about micro. How many volts are equal to 1 microvolt?
Micro is not 1,000.
1,000th?
So we're going the right way. It's smaller than 1. 1/1000th of a kilovolt would, no, a 1/1000th of a volt would be a millivolt, the lowercase m. A microvolt, that was the Greek letter
The
mu,
It's gotta
big-
be 1/1,000,000.
it's a 1 millionth, yes.
So
So
that
it's
one is
2
3
jumps
jumps.
from 1, 2.
Okay,
Are you sure it's not 3?
Yes, it's 3 jumps would be nano.
Oh, okay.
So 1 volt, and then there's the microvolt. So a micro is gonna be smaller than the volt, right?
Yes,
And then it's gonna be, so there's something in between micro, so volt, something, and then microvolt,
it
kilovolt.
goes from volt, millivolt, microvolt, nanovolt, picovolt. So
Mhm.
the milli is between the 1 and the micro.
Okay, so
A
the milli,
1/1000th of a volt would be a millivolt.
1/1000.
Like what we had with the very first, here is one. How many milliamperes is 1.5 amperes. So
And
we had the milli before.
Okay, so that was 3. So this decimal point would move 6.
Yep. And another one, if an ammeter calibrated in amperes is used to measure 3000 milliamp current, what reading would it show? So forget about all the verbiage around it, how they set
Okay.
up the question. The important thing is 3000 milliamps. What can we convert that to?
Amps.
Yes, and how many amps would that be?
So there's only one answer in there that moves it 3 decimals.
Which
I mean,
would be
3
3.
places.
yeah, 3.
Yeah, it would be 3.
So what was that, like
Actually-
6 questions maybe?
Actually, this one also moves it 3, but the other way, the wrong way.
Well, that would
Oh,
move
yes.
it 3 twice the, oh, yeah, I see what you mean.
So if you add 3 zeros to 3,000, you end up with 3 million. So
Mhm.
yes, that,
But that would go the wrong way.
Right.
because we know milli is smaller.
Mhm.
And I
Well,
think
what
this
would
may
be
be
the
the
bigger
last
number?
question.
What would be the bigger M? Because I'm gonna guess it's an M. Mega or,
This would be 3 mega amps.
okay,
So this would be
Okay.
the capital M.
okay, the capital M. Yeah, that's what I was wondering. Okay, I'm starting to get a feel for it.
I think we have a few more. If a frequency display calibrated in megahertz shows a reading of 3.525 megahertz, what would it show if it was calibrated in kilohertz? So again, forget about all the verbiage around those two numbers. We have 3.525 mega in 1 kilo. So how many is that?
3,525 kilo, because it's down 3. So you're gonna move it over 3. And you'd get 3,525
Yes,
kilos below mega, so kilohertz C.
correct. Yes, C is the right answer. And this is the last question, I think. I hope. And this is the one
Up
where we
to
actually
the
have to make
micro.
2 jumps.
1 microfarad.
Yes, it is 1 micro. So we move the decimal point 1, 2,
Other
3.
way, babe.
Oh,
Carl Heinz,
other way.
sorry.
1,
Babe,
2,
Mr. Babe
3,
teacher. Go the other way.
and then we move it 1, 2, 3 again. We end up with 1 microfarad. And this is, I think, the only one that is moving it twice.
Because if you only move it once, you end up with C, but then it's not a microfarad anymore.
Right.
I mean, then
From
it's,
micro to
yeah,
pico
you
is
gotta go
two
two
jumps.
jumps.
Yeah.
Yep.
I think we have to memorize this chart. That's what we
Yeah.
need the mnemonic for.
I was wrong. There's another one. They don't end.
Kilo, hecto, deca, deci, centi, milli, micro, nano, pico.
So we want to go from 2,425 mega to giga.
It's one move.
So is giga bigger or smaller than mega? Start there. Is giga
Giga's
bigger or smaller?
bigger.
Right,
It's
so,
bigger.
so
Right.
you're gonna
By
want a number that's,
one move. So you
you're gonna
have to
want a
move
number
it
that's bigger
3.
than 2,000.
Yeah. You have to move it over 3. So it's going to be 2.425 gigahertz.
Yes. So right answer is C.
Mhm.
Okay, I think we're done with the conversions. So may have been like 8 questions or so. I didn't count. I stopped counting after 5. But it's not too many. So you can just try to remember what the
And the
right answer is
chart.
without really understanding. If you learn the chart, you know
Turn the chart.
what the sequence of these prefixes is, then
Can you
it
go
shouldn't
back
be a
to it
problem.
again? Can you go back to it really quickly?
Yes. Can we just go through the last 3 questions? I don't think we have more than 3 questions left. And then I don't have to find my spot again.
Yep.
So what is the proper abbreviation for megahertz? So is mega the capital or the lowercase?
Capital.
Okay, so that leaves C and D. Is it capital M lowercase h or is
no.
it capital M capital H?
D.
It's D, yes. So when you look at all the questions we've had so far, there is always a capital M, capital H, lowercase z. So the right answer in this case is D. What type of amateur station simultaneously retransmits the signal of another amateur? Yes, it's a repeater. So it was one of those 2 terms that we learned today, and this is the repeater. And then what is a transceiver?
B, a unit combining the functions of a transmitter and a receiver.
Yes, so we're taking the trans from transmitter and the receiver from receiver. So it's that unit that has both in one box. And that is it for the questions of module 2. So I think there was 25 questions or so. Now let me go back to the chart.
So you guys, before you start reading the next chapter, you could just go back through chapter 2 and wrap your head around it, practice the questions a couple more times, and then move forward.
So one thing you can do.
Obviously, we're reading the chapter before.
Yes.
Okay, and we're doing 1 chapter per week?
Yes.
Yep.
Okay. If we need to back, and I apologize to you guys, I'm late to the game. I didn't read chapter 2 before we started. If we have questions at all from previous chapters, can we throw them in at the end of our, okay.
Yeah.
Thank you.
Just bring them up either at the beginning or at the end of
Okay.
class. And if you think it's not something that everybody's interested in, just shoot me an email and I'll respond to an email.
Okay, thank you.
So this is what we had for today. I know it was a lot. And it was a lot of new concepts for you. So I hope I didn't lose you. And
Clover and
that
Annika,
always
you were
come-
really quiet. where are you? Are you good? Are you in the middle? Annika, good. Clover, good. Yeah, see, this is probably much fresher in their brains.
They are used to learning.
That's their job. Their
not so
job is
much.
to learn right
Yeah.
now. Annika
Yeah.
and Clover, that's your job. Your main job in life is being a student.
Best
So-
part of your life, in my opinion.
Yeah.
Work is so overrated. Student life,
So all those questions, they're right there in the book. They're in the back, and you can just drill, or you can get onto the ham radio site and drill yourself just chapter 2 questions. And you're going to be so surprised if you do that. If you do that today, tomorrow, the next day, you're going to be like, oh my God, I know this, I know this, I know this. Yay. You're going to feel so good.
So before we go, do you guys have any questions about what we've done today or last week?
Great.
Can't hear you.
You got to put
No
that space
questions.
bar.
I'll have some next week when I do
Okay.
chapter 2. But
Okay.
I'm feeling like, as long as I remember the 3 spaces, and I'm gonna memorize the chart.
Yeah.
And keep in mind, that chapter has a whole lot of stuff in it that has nothing to do with the test. So
Okay.
this whole class, what Karl Heinz is doing, it's like he doesn't need to just teach you the test. You can just read all the questions and memorize them.
Mhm.
So it's kind of trying to find a balance between teaching some concepts about ham radio plus making sure you know the answers.
Right.
So there'll be all sorts of stuff that are in the chapters that will never show up on the test, but they give you like some concepts. So you got to pick out what's, it's like when the teacher's like, this is important, it's on the test.
Yeah.
The rest of this is just interesting, but this one you need to know.
I thought this was very interesting. I need to look it over again.
yeah, it makes
Okay.
a lot of sense to me now, because reading it and talking about it and going over that, like now I feel like it makes sense, like in the real world. Like you can read it on paper all you want, but I haven't done this stuff in years. So thank
I
you.
would also like to say Annika and Clover are the most unfidgety people. You guys, I have been moving around and I'm uncomfortable and I'm moving and I'm picking up the cat and I'm playing with my knitting and you guys are just like, boom.
They probably just have a picture of them in front of the camera and they're doing other fun stuff in the background. Okay, so if we don't have any questions, then for next week, review chapter 2 and then start to work on chapter 3. And this is unfortunately where it gets complicated. Chapter 3 is probably the most complicated chapter
Okay,
in the
good
book.
to know.
And then it gets way easier after 3.
Good
Way.
to know.
Yeah. Yeah. And I think I said that in my email. They do this so that you have a lot of time to practice those questions associated with those earlier chapters, which are harder. Once we get into the legal stuff, a lot of stuff is just obvious and we just have to review it. But you will be able to probably answer a lot of these questions without even thinking about it. The stuff that we've done today and the stuff that we will do on next Tuesday, that is a little bit different, in a different category. So that requires practice, practice, practice. But again, if you go through those questions again and again and again, eventually it will stick. And not everything, but hopefully enough so that you will get at least 26 correct answers. Okay. Have a good week, and I hope to see you all on back next Tuesday.
Thank you.
Thank you very
Bye,
much.
guys.
Bye.
Bye, guys.
Good night.
Bye, everybody.
Bye.